The statement of Galois theorem is An is simple. An is a simple for n is greater than equal to 5. So what we mean by simple, it has no proper normal subgroup. A group G is simple if it has no proper normal subgroup. Now, to prove that this An, which is a set of even permutation, is a simple. So let I take H, which is a non-identity elements. Non-identity normal subgroup of group be a normal subgroup of group An So let H be a non-identity normal subgroup of group An. So it means the bigger group is An, and this is identity, and I take some group which is greater than I. If I prove this group is equal to An, then it means An has no proper normal subgroup. Yeah, An has no proper normal subgroup. So it means An is a simple. So we claim that H is equal to An. So that is my A. Now I will use the previous three lemmas that we are proved in the previous lecture. Now since H is non-identity, since H is non-identity, it means there exists F, which is a non-identity permutation which belongs to H. And H is a part of An. So it is a product of even transposition. So even it is a product of even transposition. Now if F is a non-empty permutation, so this can be written as, if F is a non-identity permutation, so this can be written as the product of disjoint cycle. So I will use that. So if it can be written as the product of disjoint cycle, so let F is equal to sigma 1, sigma 2, so on sigma t. So this is a expression of product of disjoint cycle where sigma I are disjoint cycles with length greater than 1, such that length of sigma I is greater than 1 because it is a non-identity. Now suppose I write this is as equation number 1. Now each permutations which are disjoint, they commute to each other. So remember that if they are disjoint, they commute to each other. So we arrange these permutation in such a way that length of sigma 1 is greater than length of sigma 2 is greater than length of sigma 3 and so on length of sigma t. So since So what is the logic? Since disjoint cycles commute, since disjoint cycle commute, so we can arrange the expression 1 such that, in such a way, length of sigma I is greater than equal to length of sigma I plus 1. Or we can say that we can arrange in a descending order, the length of permutation in a descending order. So we get this kind of values. Now 4 cases arises. So there are 4 cases that arises. Case number 1. So what is the first case? So 4 cases arises. At least one of sigma I, at least one of sigma I of length greater than 1, of length greater than 3. So this is my first case. At least one of sigma I of length greater than 3. Case number 2, sigma 1 and sigma 2. Sigma 1 and sigma 2 are of length equal to 3, of length equal to 3. And naturally, number 3, so number 2 sigma 1 and sigma 3 of length 3, and number 3, which is sigma 1 is of length 3, and all others are transpositions. Transpositions mean of length 2. All other are transpositions. So number 4, all are transpositions. All are transpositions. Since an in which n is greater than equal to 5, so there are 4 cases arises. Case number 1, at least one of sigma I of length greater than 3, right? And number 2, sigma 1 and sigma 2 are of length 3. Number 3, sigma 1 is of length 3 and all other are transpositions. Number 4, all are transpositions. So we have 4 cases. So we prove our result by case 1, 2, 3 and 4. So case number 1. So case number 1. So what is the case number 1? Case number 1, at least one sigma I of length greater than 3. So I choose one sigma 1. So that is I taken sigma 1. Now it has length greater than 3. So A1, this is A1, A2, A3 and so on AR. So I choose this A1, A2, A3, so on up to AR, where R is greater than 3. So it means it has a length greater than 3. Now consider one theta which belongs to an, so that I take a1, a2 and a3, because it is a product of transposition, even transposition, so it belongs to an. So how we will check that? So this can be easily checked that theta is a1, a2, a3. Now this can be written as a1, a3, then a1, a2. So this is a product of even transposition, so it belongs to an, right? So in this way we can check that this is a of this kind. Now theta belongs to an, since H is normal subgroup, या normal subgroup in an of an. So by definition of normal subgroup, so theta f theta inverse, it belongs to H. So why? Because this theta is belongs to an, and f, which is equal to sigma 1, sigma 2, sigma 3, sigma t. So this belongs to H. So by using the definition of this, so theta f theta inverse belongs to H. Also, f belongs to, f is a permutation, so it belongs to H. Also, f belongs to H. So as H is a subgroup, so it inverse belongs to H. It implies, because it is a subgroup. So again H is subgroup, so it is closed under multiplication. So if it is closed under multiplication, so this can be written as either I used here f inverse theta into, either it can be used at the end, theta f theta inverse into f inverse. So it depends upon us, either you can use here or you can use here. So I used here f inverse theta f into theta inverse, it belongs to H. So this is equation number 1. Now my aim is to find the value of this product. So what is the product of these values? So first f inverse, so f inverse will be sigma 1, sigma 2, so on up to sigma t, right? And it inverse, since they are by using reversal law, sigma t inverse, so on sigma 2 inverse and sigma 1 inverse, right? These values. Similarly, theta inverse, basically it is a a1, a2 and a3, these values, and it inverse, which is equal to a1, a2, a3 inverse, this cycle is equal to a3, a2 and a1. So in a reverse way. So here you can write the value of sigma inverse. So this will become, which is equal to sigma t inverse continue sigma 2 inverse. Now what is the value of sigma 1 inverse, which is ar, ar minus 1, so on a2 and a1, these values, right? Now we know the value of f, and also we know the value of theta. Now I substitute the all the values. So first is f inverse. So first is f inverse, and then theta, then f, and then theta inverse. Now this value is equal to first F inverse, so which is this sigma, this is up to T, so sigma T inverse, sigma T minus 1 inverse, so on sigma 2 inverse, and then which is a inverse of sigma 1, that is equal to AR minus 1, so on A2 and A1, this values. Now after that theta, so what is theta? Theta is A1, A2 and A3. So after that F, what is F? F is this values. So first it is sigma 1, so which is A1, A2, so on AR, and then sigma 2, sigma 3 and sigma T. After F, so this is F, theta inverse. So what is the theta inverse? A3, A2 and A1, this are. Now since all the cycle are disjoint, so they commute with each other. So it commute with this and then it goes to at this place. When sigma 2 goes to at this place, it become identity. Similarly, sigma 3, this goes to at this place, it becomes identity. And sigma t when goes to this place, so it becomes identity. Since the then permutations are, since the cycle are disjoint, so they commute to each other. If they commute to each other, then sigma 2 shifted at this place become identity. Similarly sigma 3 and similarly sigma t. So what we get? We get this values, which is a cycle AR minus 1, so on A2 and A1, these values. After that A1, A2 and A3, and after that which is again A1, A2, so on AR minus 1, AR, and after that A3, A2 and A1. So I will find the product of these 4 cycles. So how I will find the product? I write here the product. Now how will I find? I start from the right hand side. From this I have 4 steps: 1, 2, 3 and 4. So step number 1, A1. So A1 goes to A2. So that is in step number 1. Sorry, A1 goes to A3. So this goes to A3 in step number 1. Now in step number 2, it goes to A4. A3 goes to A4. Here no A4, so it goes to A4. Here A4 goes to A3, right? So it means my first step A1 goes to A3. So cycle complete, and not cycle complete, A1 goes to A3. Now next step. Now I start from A3, which goes to, in this step A2, in this step A3, and in this step A1, and in this step AR. So this goes to AR. After that, this is AR. So AR goes to at this place. At this place, AR goes to AR. At this, it goes to A1. At this place, it goes to A2. At this place, it goes to A1. So AR goes to A1. then cycle complete. Now here 1, 3 and A are, they are used. The remaining are from A2 to A2 to AR minus 1. So I start from A2. So A2 goes to A1. From this it goes to A2. From this it goes to A3. From this it goes to A2. So it become identity, right? So it is finished. Now next is A3 already, now A4. So A4 here goes to A4, here A4 goes to A5, here A5 goes to A5, here A4 goes to A4. So again it becomes identity. Similarly, A5 it also goes to identity, A6 and at last AR minus 1. Now check that AR minus 1 it goes to AR minus 1 in first step. In second step it goes to AR. It goes to AR. So in this step it goes to AR and in last step it goes to AR minus 1. So all the element becomes identity. So what is this? It is a 3 cycle which belongs to H, because that product belongs to H. So this 3 cycle belongs to H. So as we know that if H contains a 3 cycle, then H is equal to AN. Then H is equal to AN. So which prove our first case. So in this way we can prove from all the 4 cases. So first case, that is proved in this way. Now same method I will apply to case number 2. Now what is case number 2? So in the case of case number 2, so here the first 2 element are of length 3. So first 2 element are length 3. So I take sigma 1 which is equal to A1, A2, A3 and sigma 2 which is equal to A4, A5 and A6. So all are transpositions. Then its order is 1 because all are transpositions. That's why its order is equal to identity. So 1. Now consider theta which consisting 3 element. So I take it as you can choose any 3 element. So I take it as A5, 6 and 1. A5, A6 and A1. So this belongs to AN, right? So what is F? F is equal to, which is of sigma 1, sigma 2 and sigma 3 and so on up to sigma t, this value. Now again, since H is normal in G, so we know that theta F into theta inverse, it belongs to H. Why? Since H is normal in G, normal in AN as per in case number 1. Again, if F belongs to H, so it implies F inverse belongs to H by using the binary composition, product binary composition. Again, F inverse into theta, F theta inverse, it belongs to H because H is subgroup of group AN, so which is a subgroup of group AN, this product. Now find this product. So what is F? So we know that, so F is equal to A sigma 1, A1, A2, A3 and A4, A5, A6, then sigma 3, so on up to sigma T, this values. So what is F inverse? First find F inverse. So this will become sigma T inverse and so on sigma 3 inverse by reversal law, by using the, so first it will be if this inverse, which is A6, A5, A4 and then it inverse A3, A2 and A1, this values. So what is theta inverse? So theta inverse, which is equal to A1, A6 and A5, right? So by A1 reversal law, its inverse. Now this product F inverse, so what is F inverse? Then theta into F into theta inverse. This value is equal to. So what is the F inverse? So this is a sigma T inverse sigma 3 inverse, which is equal to A6, A5, A4, which is A3, A2, A1, this values, and then theta, so which is equal to, so what is the value of theta? A5, A5, A6, A1, this values, and theta, F inverse theta, then F, which is sigma 1, sigma 2. So substitute the value of sigma 1 and sigma 2 and that value is A1, A2, A3. So that value is A1, A2, A3, A4, A5, A6 and then sigma 3, so on up to sigma T. So this is a value of F, right? After that theta inverse, so which is a A1, A6, A5. Now this element sigma 3, all the permute cycles are disjoint. Not all the, so these cycle are disjoint with these cycle. So it commute with all these cycle and at this place it becomes identity. Similarly, next will become identity and similarly sigma T becomes identity. So what we get? We get A6, A5, A4, these values, A3, A2, A1 at this place, then A5, A6, A1 and A1, A2, A3 at this place and then A4, A5, A6 and last A1, A6 and A5, this values. Now my aim is to find the product and this product belongs to H. So how we will find that? So this is equal to this values. Now start from this step. I take A1. So A1 in the first step, it goes to A6, right? In the next step, it goes to A4. 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 In the next step, it goes to A6. So A1 goes to A6. Now start from 8, 6. So what is A6? A6 goes to A5. A5 A5 goes to A6, and then A6 goes to A6, then A6 goes to A1, and A1 goes to A3, and A3 goes to A6 goes to A1, A1 goes to A3, A3 goes to A3, right? So A6 goes to A3. Now next A3, which is from this, A3 goes to A3, it implies from this A3 goes to A3, and here A3 again goes to A3, here A3 goes to A1, here A1 goes to A5, here A5 goes to A5, and here A5 goes to A4, and here, so A1, A6, and there, so I repeat once again, A3 goes to A3, A3 goes to A3, A3 goes to A1, A1 goes to A5, A5 goes to A5, A5 goes to A4. So this cycle is up to this. Now start from A4. I directly use this. Now A4 goes to A4, A4 goes to A5, A5 goes to A5, A5 goes to A6, A6 goes to A6, A6 goes to A5. So this goes to A5. Now start from A5. A5 goes to A1, A1 goes to A1, A1 goes to A2, A2 goes to A2, A2 goes to A1, A1 goes to A1. So this cycle is complete. Now it is a product, it is a cycle of A1, 6, 3, 4, 5. Now I start A2. Now this from A2. A2 goes to A3, A3 goes to A3, A3 goes to A2, and A2 goes to A2. So it means A2 goes to A2 means identity. Now start from A7. So there are 6 elements. So this contains a cycle of length 5. So it is a cycle of length 5. Now this cycle of length 5 means greater than 3. So it belongs to H, since F inverse theta, F theta inverse belongs to H. So it belongs to H. Then by case number 1. So by case number 1, H contain a cycle of length greater than 3. So it implies H is equal to AN. So which prove our case number 2. Now case number 3. So in the case number 3, sigma 1 and sigma 2, sigma 1 is of length 3 and each sigma I are transposition and other are transpositions. So let sigma 1, which is of A1, A2, A3, and sigma I, where I is running from 2, 3 and so on up to T, are transpositions. Transposition mean its square is equal to identity. Now what is F? So F is equal to, which is equal to sigma 1, sigma 2 and so on up to sigma t, and it belongs to H. So what is H? H is subgroup. So F inverse also belongs to H because H is subgroup. Now what is F inverse? F square, which is equal to sigma 1, sigma 2, so on up to sigma t raised to power 2. Since all sigma are disjoint, so it will become sigma 1 square, sigma 2 square and so on up to sigma t square. Since sigma I, these are transposition, so it's raised to power 2, which is equal to identity for I is running from 2, 3 so on up to t. So it becomes F square, which is equal to sigma 1 raised to power 2. Sigma 1 means A1, A2, A3 raised to power 2 means A1, A2 and A3. So this is a product. Now what is the product of these cycle? Now these are not disjoint. So these are not disjoint. So first I start from A1 from right hand side. The A1 goes to A2, A2 goes to A3. So it becomes A3. Now again start from here. Now A3 goes to A1 by white and A1 goes to A2. So this is goes to A2. Now start from A2. A2 goes to A3 and A3 goes to A1. So it means A2 goes to A1. So this cycle is complete and it belongs to H. Again H contains a cycle of length 3. So it implies by case number 1. So H is equal to AN. So it contains a cycle of length 3. So it H equal to AN. Now case number 4. So what is the case number 4? So in this case, sigma 1 is of length. So in this case, sigma 1 and sigma 2 are transposition, and in this case all are transpositions. If all are transpositions, so I take sigma 1 and sigma 2. So this is A1, A2 and what is sigma 2, which is A3, A4, right? So what is F? F is equal to sigma 1, sigma 2, so on up to sigma t. And what is F inverse? Which is sigma t inverse and so on sigma 2 inverse, sigma 1 inverse, right? Now consider theta in this case. So we can choose any 3 element. So I choose here A3, 4 and 1. So A3, A4 and A1. So F belongs to H and theta belongs to AN. H is a normal subgroup of AN. So it implies F theta inverse belongs to H. Again F belongs to H. It implies F inverse belongs to H. So H is closed under multiplication. It implies F inverse theta F theta inverse belongs to H, this values. So this product belongs to H. Now find the value of F inverse theta F theta inverse. So what is F inverse? First, then theta, then F, then theta inverse. So this can be written as, so first F inverse, which is sigma t minus 1 so on up to sigma 3 raised to power minus 1. Then sigma 2 inverse, which is a A4 A3. Then sigma 1 inverse, which is A2 A1. So after it is 1, after that the next term is F, after that the next term is theta. So what is theta? Theta is A4 A3 A4 and A1. And what is next F, which is sigma 1 A1 A2 A3 A4, then sigma 3 so on up to sigma t. So after that theta inverse. So what is theta? So theta is A341. So A1 A4 and A3. So it is a theta inverse. So what is theta inverse? If I take theta is A3 A4 A1, so it is A1 A4 and A3. Now since these permutation are disjoint to these permutations, so this will shifted to this place and it makes it identity. Similarly next, and at last this will shifted to at this place, then it makes the identity. So remaining terms are which are equal to, so this values A4 A3, then A2 A1 A3 A4 A1 A1 A2 A3 A4, then A1 A4 A3. So these are terms. Now this product belongs to H. We know that it belongs to H. So what is this product? So first I check. So I start from A1. This is A1, right? From this. So move in this way. A1 goes to A4. A4 goes to A3. A3, no A3. A3 goes to A4. A4, A4 goes to A3. So at end it becomes A3. Now start from A3. So A3 goes to A1, no A1. A1 goes to A2, no A2. A2 goes to A1. A1 goes to A1. This cycle is complete, right? Now start from A2. From this, no A2, no A2. A2 goes to A1. A1 goes to A3. No A3. A3 goes to A4. So this is a A4. Now start from A4. A4 goes to A3. A3 goes to A4. No A4. A4 goes to A1. A1 goes to A2. A2 goes to A2. This cycle is complete. So this product belongs to H. So what is it is a product of two transpositions. So by second lemma that we did in the previous lecture, if H contains a product of two transpositions, then again H is equal to AN. Again H is equal to AN. So it means AN is a simple for n is greater than equal to 5. So this is very important result to prove that AN is a simple when n is greater than equal to 5.